So today we are going to talk about inverse functions. We're going to finish up section 2.8, which I think you will find at least a little bit interesting. Unfortunately, I really have to use the bathroom, so I'm going to be right back. Alrighty, we're back. So last time we hinted at this concept of an inverse, but we haven't really played around with it too much. Today we're going to see all the gory details. I want to remind you, as I must, that our next class, this Thursday, we're going to have a test. That'll be our first exam of the semester. I have here a bunch of emails from people who want to take the test in the testing center. I've been working through it. I had 54 emails when I woke up this morning. So it's just taking me a little bit of time to get through that, but I will be making your reservations today. If you ask to take the test at the testing center, I will be getting you all squared away today, and I'll reply to your emails as I get those appointments confirmed with the testing center. This, as always, is MAC1140, section 009. That is a pre-calculus class. And today is the 21st of September, 2021. And what we're doing today is learning about inverse functions. Which is section 2.8, the last section that is on our test. I have opened for you some new stuff. This is section 008, but they've got pretty much the same schedule you do. So you'll notice a few things since our last meeting. Last time I opened up quiz 2 right after we met, and I today opened homework 8 for you. And this is the last assignment you're going to have before the test. Also, if you go to your modules, I had some people tell me they wanted extra review material, like stuff in addition to the web assign. I opened up my physical copy of the book and scanned out the whole chapter 2 review. It's quite a large thing. And you are by no means required to do this, but it can be a really nice way to take a kind of cursory glance at the important topics from the chapter. Now remember, this test covers chapters 1 and 2. Chapter 1 is preliminary stuff that you've seen before, hopefully. So I did not scan that in. This is just the chapter 2 review, but that's most of the stuff on this test. You see here, there's lots of stuff about moving graphs around, even and odd functions, compositions, domains, inverses. These concept check questions are very good. I feel like if you have good answers for all of these, then you'll be in good shape for my true-false questions. And then there's plenty of exercises for you to run through. And plenty more exercises for you to run through. And plenty more exercises for you to run through. So if you're wanting extra study material, here we go. We got lots and lots of it. Again, you're not required to do this. This is just there for people who want more practice with a particular topic. The things you are required to do, of course, are the things in WebAssign. So make sure you're getting the homework done and make sure you're understanding the homework. If there's something in there that you're not feeling comfortable with, that's something you should bring to me in office hours. We can talk through it there and make sure whatever that one little thing is that you are super comfy. I know plenty of you have submitted extension requests. I cleared these out yesterday. These 36 are fresh since yesterday afternoon. I'll be knocking those out as soon as I can today. All right. So the test is Thursday, our next class meeting. We have a test. If you're going to take the test in the testing center, you would prefer to take the test in the testing center, you need to send me a Canvas message, and I will make an appointment for you there. Otherwise, you're going to be taking the test with us here online. And remember, in order to do that, you're going to need to sign into Zoom on your phone. You'll need to sign into Zoom on your phone before launching HonorLock, and you have to wait till you get the OK from me in Zoom to start the test. All right, let's do it. So the big question is, given a function f, can we find another function which exactly undoes whatever it is that f does? So remember, you can think of these functions as like machines, right? In fact, the machine diagram is a useful way to think about inverses, perhaps not the most useful way, but a useful way. So remember how this works. We think of f as like a machine on an assembly line or in a factory. X's come in, f of x's go out. So, f maybe is the add 3 machine. It takes in x, adds 3 to it, and sends x plus 3 out. That would be the function f of x equals x plus 3. F of x may be the squaring function. So it takes a number x in, squares that number, and sends it out. So 2 comes in, 4 goes out. -3 comes in, 9 goes out. Even more abstractly, here's one of my fun metaphors for this. Imagine f is a machine at like a recycling facility, right? The facility recycles aluminum cans, whatever. And maybe the thing that comes in are the cans to be recycled. And the function f, this machine, burns off the logo, scrapes off all the paint, whatever. And then a blank can, just a shiny silver aluminum can, comes out. So Coke, Pepsi, whatever cans come in, blank cans go out. That would also be a function. Another numerical example, f of x could just be the function f of x equals 2. So 5 comes in, 2 goes out. 10 comes in, 2 goes out. -pi comes in, 2 goes out. No matter what comes in, it sends out the number 2. The notion of the function which undoes f in the machine diagram world would be running this machine backwards. So the concept of undoing f here with this machine diagram would mean running the machine backwards. Right? So if f is the add 3 machine, right? 2 goes in, 5 goes out. 5 goes in, 8 goes out. 10 comes in, 12 goes out. If you ran that backwards, then 12 comes in, 10 goes out. Or 8 comes in, 5 goes out. Or 13 comes in, 10 goes out. Right? We would just turn the belts around to run the other way. Sometimes that works really well. Like the add 3 machine is easy to invert. It becomes the subtract 3 machine, right? You just run the machine backwards. Instead of adding 3 as you run through this way, you subtract 3 as you run through the opposite way. The soda scraping label thing doesn't work quite like that, right? So like Coke, Sprite, Pepsi can comes in, blank aluminum can comes out. If I wanted to run that backwards, then a blank can would have to come in. I would have to reattach that logo or label and then send out the Coke, Sprite, Pepsi, whatever. The problem is that the burn the logo off machine outputs the same thing for all of those different inputs. So over here, I just have a pile of shiny silver aluminum cans. If I pick one up and try to run it backwards through that machine, I just flip the switch to have the machine run backwards. The fucking thing doesn't know to paint Coke or Sprite or Pepsi. It has no idea what logo to paint on the can when you run it backwards, because that blank silver can nowhere says Coke, nowhere says Pepsi. The machine doesn't know how to run backwards. because it doesn't know which output came from which input. The burn the logo off machine destroys information. It takes in these inputs that have information. They have a particular logo on them, and it burns that logo off and it outputs a blank can. So there's no way to say which output goes back to which input. There's no way to say which blank can should get the Coke logo on it when you run backwards, or which blank can should get the Sprite logo or Fanta logo, whatever. That issue, where all the different inputs end up going to identical or the same outputs, is the main challenge in answering this question. Can we find another function? The answer is yes, sometimes, if the original function is sufficiently nice. And the sense in which a function can fail to be nice is if it destroys information in exactly that same way that I just described. The outputs no longer tell you, like you can't tell looking at the output which input it came from. Another example of a machine that would have that issue is the 2 machine, right? I described, whatever number comes in, it always spits out 2, right? That's the constant function f of x equals 2. 1 comes in, 2 goes out. 2 comes in, 2 goes out. 3 comes in, 2 goes out. 5 comes in, 2 goes out. 10 comes in, 2 goes out. Over here, you just have a fucking pile of 2s. And I don't know which one of those 2s came from 1. I don't know which one of those 2s came from 10. So I can't run that machine backwards because the outputs don't have any information about which input they came from. The function f destroys that information. All right. Soraya, I see your message. Let me reply to that at the end of class. Another way to kind of try to wrap your head around the problems that can exist here is to think not in terms of machine diagrams, but mapping diagrams. You guys remember those? So I have a set over here, which is like the domain. And I'll just say this has a few things in it, like 1, 2, and 3. So here's the domain for my function. It just has those 3 numbers in it. All my other colored pens go. And over here, I have the range, and maybe this is like 7, 5, and 13, whatever. They don't even have to be numbers. And the function f sends 1 to 7, sends 2 to 5, and sends 3 to 13. This is f. To describe the function which undoes f would be to describe the function that sends this output back to the input from which it came. So function notation here, we would say f of 1 here is equal to 7. Because f sends 1, the input 1, to the output 7. F of 2 here would be equal to 5, because f sends the input 2 to the output 5. And f of 3 is 13 for the same reasons. To cook up or describe the inverse here would just mean to turn these arrows around backwards. So 7 goes back to 1. Oh, sorry, 7 goes back to 1. 5 goes back to 2. And 13 goes back to 3. So the purple here, I hope you can see those colors well. The purple here would be f, and the notation is a little -1 superscript. It's not a power. It has nothing to do with the power, but we call it the inverse function. Okay, and I'll define it in rigorous terms for you in just a second. But the idea is that the purple undoes the black. Whatever the black does, send 1 to 7. The purple undoes, send 7 back home to 1. And in the function notation, we would say f inverse of 7 is 1. F inverse of 5 is 2. And f inverse of 13 is 3. So it's a little easier to visualize the inverse mapping in a mapping diagram than just saying run the machine backwards. But even better, the mapping diagrams allow us to investigate that problem I discussed a second ago. So here, the undoing function, which I've called f inverse, is itself a function. Right? It's only got these three inputs. All the outputs for the original become the inputs for the inverse. And each input over here, if you think about this as an input for the inverse function, gets sent to only one output. And that's because the black function, the original function, was kind of nice. Right? This is like it's not the add 3 function, but it's doing that same sort of thing where every input goes to one and only one output. If you think about the mapping diagram for that logo burning function, or even just the constant function 2, just for fun, say it's the constant function 5. So f sends 1 to 5, sends 2 to 5, and sends 3 to 5. And now I've got a problem. See here, f of 1 is 5, f of 2 is 5, and f of 3 is 5. So what is f inverse of 5? Well, if we kind of follow the patterns here, f of 1 is 5, so f inverse of 5 should be 1. But also,
sorry,
go ahead.
It would work the same for a parabola, right? Kind of like not necessarily a straight line being all 5s, but if it kept curving and landing on the same like y value multiple times, you couldn't necessarily reverse each one of those, could you? If you had like a large parabola that went up and down multiple times, like had multiple turns.
Yeah, you're getting at precisely the issue we're trying to confront here. And that's
Cool.
that if a function sends multiple inputs to the same outputs, defining the reverse of that function can be a very real challenge. So here, reasonable candidates for f inverse of 5 would be 1, 2, and 3. But if something sends 5 to all of these, sends 5 to 1, sends 5 to 2, and sends 5 to 3, then that thing is not a function. Here, the inverse mapping sends 5 to 1, sends 5 to 2, and sends 5 back to 3, which means it's not a function. Right? A function has to send each of its inputs to different outputs. You cannot send the same input to multiple different outputs. And the inverse mapping here would send the input 5 to 1. It would send the input 5 to 2, and it would send the input 5 to 3. So the purple in this second picture is not a function. And we, in this class, really want to focus our attention on functions because, like when we're talking about increasing and decreasing, I want to know where I am on the graph just by specifying the input. It's very important that each input only goes to one output. For the original function f, that's not a problem. It's true that each input is going to only one output. They're all going to 5, but 1 only gets sent to 5. It doesn't also get sent to something else. 2 only gets sent to 5. It doesn't also get sent to something else. And 3 gets sent to 5. But the inverse mapping, the inverse relation here takes the input 5 and sends it to all 3 of those outputs. And that's not allowed, right? That's not a function. Functions can't do that. So the question becomes, what is it about this thing, or the logo burning machine, that makes the inverse process not nice? Or what is it about mappings like this that make the inverse nice? And Gavin pretty much hit it on the head there. He said parabolas would have this same problem because they send different x values, different inputs to the same y values. So if you try to send those outputs, y values, back to the x's from which they came, you're going to end up forking inputs to multiple outputs, which is not okay. The terminology that's used to describe this sort of behavior, the good behavior, is called one-to-one mappings. One input goes to one and only one output, and also each output comes from one and only one input. This guy down here, the black, the original function going from left to right, is called a 3-to-1 mapping, because I've got 1, 2, 3 different inputs all getting mapped by the black function to the one output 5. 3, 2, 1. So the functions that we can invert are the 1-to-1 functions. A 2-to-1 function or a 3-to-1 function are bad news for inverses, because the inverse relation is automatically not a function. And for those of you currently taking trigonometry, your trig functions, they're much worse, right? They are super duper not 1-to-1. Because your trig functions are periodic, they're not just 2-to-1 or 3-to-1, they're infinity to 1. For every output in the range of one of your trig functions, there's infinitely many x values that get sent to that output. Those are ultra not nice. Right? Those would be infinity to 1 functions, and frankly, fuck that shit. I'm going to show you a way to get around this issue. I'm going to show you a way to get around the issue of a 2-to-1 or 3-to-1 or even infinity to 1 function. But first, I want to show you how to invert functions when they are 1-to-1, and even before that, how to detect if a function is 1-to-1. And even before that, let's go ahead and define what this thing is that we're talking about. So we've been saying the word inverse, but I haven't defined it for you. Let's define it. I'm actually going to define 1-to-1 before we do that, because the definition of inverse is easier if you do this first. So definition. A function f is called 1-to-1, which I'm going to abbreviate as 1-1 like this, because it takes some time to write, provided f sends different inputs to different outputs. All right, that's the language that your textbook uses, and it's fine, it's correct. You could also say that every input gets its own output, that every output comes from its own input, or that every input has a unique output in the range associated with it. Algebraically, this means if I have two different inputs, x1 and x2, and they're not equal to each other, if I have x1 and x2 being different, distinct inputs, then f of x1 needs to be different from f of x2. Right. Distinct inputs like 4 and 7 have to have distinct outputs. They can't both be mapped to the same thing. One more definition. Given a 1-to-1 function f, there exists a function, turns out to be unique, a unique function f inverse which exactly undoes f. In the sense that if f of x is equal to y, f, in other words, if f sends the input x to the output y, then that is equivalent to saying f inverse of y is x. So if f sends x to y, f inverse sends y back home to x. And that very last thing that I wrote there can itself be re-expressed in terms of the composition operator. And I'm going to do that in a second. I just want to give you a tenth of a minute to digest this. So any questions on what's being said in these definitions? Okay, so that is our IE. I'm going to restate this in terms of composites. F inverse of f of x. Remember what this means. This means like f inverse of f of x, like this, should be what? This thing. So the x in the very, very inside is an input for f. F of x is the output associated with the input x under the function f. And then I want to do f inverse to that. So this thing, which is exactly supposed to undo f of x, when I apply both of them to x, what should I get out?
Wouldn't it just be f of x, like the original form?
It should just be x itself. X itself. So imagine f is the add 3 function, right? F takes whatever you feed it and adds 3 to that. Then the function which undoes that would be the subtract 3 function. So if you start with some number, add 3 to it, then subtract 3 from that, you're going to get that number back. One of the famous analogies here, and I'll explain why a little later, is called the socks and shoes rule. If x is my bare foot and f is the function put on your socks and shoes, then f inverse would be the function take off your shoes, then take off your socks. So if I have a bare foot, I put on the socks and shoes, then I take off the shoes and take off the socks, I'm going to get the bare foot back. And this operator should work in both ways, in both directions. In other words, if I do f inverse first, that means I'm starting here with elements in the range of f, but then I undo f and redo f. In other words, I take f of f inverse of x. This should also send me back to x. First line, x is an element of the domain of the original. In the second line, x is an element of the range of the original. But the thing to keep in mind is that f and f inverse should exactly undo one another. So if you do both of them to something, you get the thing you started with back. This is the standard definition. And it's equivalent to this, which is what your textbook writes. So we know what an inverse is now, and we know under what conditions we can expect an inverse to exist as a function itself. The big question is, how do you find the damn thing? Even before that, I should ask, how do you know, since I can only find inverse functions for one-to-one functions, how do you know if the function you're starting with is one-to-one to begin with? right? This definition here says, given a one-to-one function f, there exists blah, blah, blah. So we have to be able to first check, is f one-to-one? If f isn't one-to-one, I can't do this. So how do you know if a function sends different inputs to different outputs? Gavin hinted at it earlier. It was, do you have points on the graph with the same y values? If you have two different points on the graph with the same y value, that means the x values of those points, those inputs, are getting mapped to the same outputs, same y value. The general term for this is called the horizontal line test. Which says if any horizontal line hits the graph y equals f of x in more than one place, then f is not one-to-one. And the way to think of this is precisely as Gavin said. I'll draw for you a picture here. Maybe I have a function whose graph looks like this, something kind of parabolic. And you take some, you notice there's 2 points on here with the same y value, right? Like these two. You draw a horizontal line, and you notice that that horizontal line hits this graph more than once. According to the horizontal line test, this should mean the function is not one-to-one. Well, why is that? Here is, I'll call this x1. Here is, I'll call this x2. The point here is x1 comma f of x1. And the point over here is x2 comma f of x2. Clearly, x1 and x2 are different numbers, right? They're x values, and they're at different places on the x-axis. So x1 is different from x2. But since the points live on the same horizontal line, they have the same y values. i.e., f of x1, the y value here, is equal to f of x2, the y value here. And if you compare that with the definition of a one-to-one function, which says if x1 is different from x2, then f of x1 must be different from f of x2, you have a clear violation, right? This x1 is different from this x2, but their y values, f of x1 and f of x2, are equal. That contradicts the definition. So if any horizontal line hits your graph in more than one place, automatically your function violates the definition of being one-to-one. And the contrapositive is kind of the thing we're looking for. So if no horizontal line hits your graph more than once, then automatically your function is one-to-one. So in other words, to test a function to see if it's one-to-one, it's useful to have the graph. If you have the graph, you can answer the question right away. If you have a table or a mapping diagram, you can answer it just using the definition. Do different inputs go to different outputs? You can check at a table. Okay, does 1 go to 5 and also 3 go to 5? Okay, not one-to-one. Similarly, if you have a mapping diagram, like I showed you at the start of class, do you have multiple arrows from the original sending different inputs to the same output? Okay, not one-to-one. But most of the time when we do this, we're doing it with the graph, and the horizontal line test is the tool. So you just imagine drawing a shitload of horizontal lines. If any of them hit the graph more than once, you're not one-to-one. If none of them hit the graph more than once, then you are one-to-one. Okay, so we know how to tell if a function is or is not one-to-one. And we know that one-to-one functions have inverse functions. So if you know you have a one-to-one function, how do you find its inverse? I'm going to outline a 5-step process for you. One of those steps is going to be a little weird in our first example, and then I'll do another example to kind of explain where that step comes from. So I'll ask you to kind of just go with me on this at first. How to find F inverse. 5 steps. First, write y for f of x. So maybe you have f of x equals 2x minus 3. And then you're going to write y equals 2x minus 3. Then solve that equation for x. I know this might be a little different than what you've heard in high school or other algebra classes. Just go with me on this. I promise you this is the smart way. Here's the weird step. Consider any domain restrictions. So remember what we said, only one-to-one functions have inverses? Well, being one-to-one depends on your domain. If I think of the parabola x squared, it's definitely not one-to-one. It fails the horizontal line test on its normal domain. But if I restrict its domain and throw away half of that parabola, the new thing could be one-to-one. The first example we're gonna do, you're not gonna have to worry about this. The second example I will do, we will worry about this. So for now, just put this in your notes. We will come back to it. We're not gonna stress about it at first, but I promise you I will explain. Write y for f of x, solve for x. Consider any domain restrictions, then swap x and y. When they teach you this shit in high school, they usually make that the first step. They're wrong, just wrong. And again, it's got to do with this third step, and I will explain exactly why this should be done after solving for x. So write y for f of x, solve for x, worry about domain restrictions, then swap x and y. And now finally, f inverse of x is y. So you can swap, or you can replace y by f inverse in the last step. Right, this is your 5-step procedure for finding the inverse of any invertible function. Let's do it. And like I said in this first example, step 3 isn't going to be relevant because I'm going to start with a function that is one-to-one. We won't need to restrict its domain. I'm going to say find f inverse where f of x is x over x minus 2. And you may ask, and I would agree, is this one-to-one? It's not super duper obvious. Hopefully you have learned how to graph functions like this in the past. It is a normal part of college algebra, but I'm not going to assume that you remember that right now. Instead, I will just graph this for you in Desmos, and we will use the horizontal line test to verify that it is one-to-one. All right. Here is my function, and I'm going to write add slider, get rid of the x. All right, so I'm using my Desmos tool here to run the horizontal line test. As I move this horizontal line around, does it hit the graph in more than one place? Well, up here, it's only hitting this portion of the graph. As I move down here, we might get worried, but if you look here, it's still just hitting the graph in this one place. It doesn't hit it anywhere over here. And as I move further and further, it still only ever hits the graph at one place. Once this red line is below y equals 1, the place it hits is on the left piece now. As we go down, it still only hits the graph in that one place. The only spot where you might be worried is like right around here. But if this red line is above y equals 1, it will hit on the right. If it's at exactly y equals 1, it won't hit the graph at all. And this is something called an asymptote. We'll talk more about these a little later. And then if it goes below 1, it's going to hit the left branch over here. So this graph does pass the horizontal line test. So the first thing your step 0 here is check that f is 1-to-1 using the horizontal line test. And we just did that. It is. Now we're ready to begin our procedure. We know we have a 1-to-1 function, so we can follow this 5-step procedure to find the inverse. My first step, write y for f of x. So that's y equals x over x minus 2. My second step is to solve this expression for x. Can anybody suggest a good first step here if I want to solve this for x?
X plus 2.
Well, so I need some sort of algebra process. So what am I going to do to both sides? We're going to do a bunch of stuff to both sides. What's that first step going to look like? I'll tell you a little story. So in my pre-calculus class, I took 1147 back in the Stone Age. My professor ran through the definitions and things, and then without ever showing me an example like this, put this on the test. And I remember coming very close to crying during that test because I knew what to do. I knew I needed to solve this for x, but I couldn't for the fucking life of me figure out how to do it because there's an x up here and there's an x down here. And how do I get the x's alone? There's a trick. Does anybody see any sort of moves they would like to try? All right, I'll spoil it for you. What we want to do is get every term with an x on one side and every term that doesn't have an x on the other side. And the first step towards that is to multiply both sides by x minus 2 to get this out of the denominator. So I'm going to cross multiply. I'll multiply both sides by x minus 2. That will give me x minus 2 times y on the left. And on the right-hand side, x minus 2's cancel there, and I just have x. So this is the first step. Now there's an x over here, and it's attached to a y, because this y needs to distribute. And there's an x over here. And my goal is to get every term with an x on one side and every term that doesn't have an x on the other side. Yeah, almost, Suzanne. We're really just going to multiply both sides by x minus 2. So as long as we do it on both sides, we don't need to multiply by 1. But we're going to multiply both sides by x minus 2. Beautiful. Okay.
Honestly, just always assumed that the y was equal to 0. I didn't realize we could just keep the y in there and use it like that. That works
Yeah,
great.
in fact, we have to here. So if you were to replace y by 0, you're going to get out of this just one solution for x. You're going to get the one x value where the graph of this function outputs 0. You're going to, what that would find for you is the x-intercept. And we don't want a point. We're looking to rearrange this so x is a function of y. So we leave y as y, multiply both sides by x minus 2. Now I want to get x alone. To do that, I need to distribute this y and then bring this guy to hang out with his buddy here. So this is going to be xy minus 2y equals x. I've got an x here and an x here. I want those guys together. This guy, the minus 2y, he doesn't have any x's. So I'm going to push him to the other side. So xy stays on the left. I'm going to subtract this x over here. And I'm going to add this 2y over here. Now, every term which has an x is on the left, and every term which doesn't have an x is on the right. I've separated out terms that have x's and terms that don't have x's. The reason that's nice to do is because now I can factor an x on the left. When I factor that x, this xy becomes a y, and this minus x becomes a minus 1. So I get x times parentheses y minus 1 is equal to 2y, still just chilling over there. And you see now we're very close to having this solved for x. I can divide both sides by y minus 1, and that will just leave x on the left. So x is equal to 2y over y minus 1. So that's step 2 done. Now step 3, let me annotate this. Step 3 is only necessary if the original is not 1-to-1. So I know I said you can only invert 1-to-1 functions. There's a little asterisk there, and step 3 is going to be the asterisk. This function was 1-to-1. So we don't need to worry about step 3. I'll still make a little note of it here. I'll say step 3. There were no domain restrictions. Because f is 1-to-1. And again, I know this feels a little bit weird at the moment, but I want to do an easy example first, then we'll do one where we have to worry about that shit. So for now, we just say not necessary. Step 4, swap x and y. So I've got x equals 2y over y minus 1. When I swap x and y, that now says y equals 2x divided by x minus 1. And then finally, step 5, y should now be f inverse of x. So I just relabel this as f inverse of x equals 2x over x minus 1. And this is your inverse function. The original function in black up here is 1-to-1, so it has an inverse, and that inverse is this guy in purple here. Or so I claim. Now, if you don't trust me, or if the problem asked you to verify that you have found the inverse, we would need to check the definition. Remember what the definition was. This stuff. This is how you check or verify. We said this in words, but I'm going to put it back here, that two functions are inverses. Right? So I'd like to run through that with you because there are plenty of homework problems that just ask you to do that. It's a reasonable possible test question. And it's also a nice way to check our work here. So I think I found the inverse. I think this is the inverse of this. If I want to check that, I'll write this as a separate example. Verify that f of x equals x over x minus 2, f inverse x equals 2x over x minus 1 are inverses. The thing to do then, we must show that f inverse of f of x equals x, and f of f inverse of x equals x. I think I'm just going to do the first. I think I'm just going to do this for you guys because each of these would take some time and there's not anything magical that you learn from doing a second one. It's just more of the same. But if on a test or in a homework I ask you to verify that two functions are inverses, this is what it means. It means you need to show that this is true for those two functions. There are functions where this works and this doesn't. It's weird, right? You wouldn't think that, but it's true. Something where the first one works and the second one doesn't would be called a left inverse. and something where the second one works, but the first doesn't would be called a right inverse. And when we talk about matrices and matrix algebra, we will encounter those. But for now, it's not the case. So let me check the first. All right. F inverse of F of X is by definition what you get when you take F inverse and plug into it F of X. And for these functions, that is F inverse of X over X minus 2. And there's going to be quite a bit of work with fractions to do here. What is that? Well, that means I'm going to take the formula for F inverse here, and everywhere there's an X, I'm going to write X over X minus 2 instead. So this is 2 times X over X minus 2 divided by X over X minus 2 minus 1. So that's the thing I need to simplify. Hopefully this simplifies just to X. If these two functions are actually inverses, this should simplify to X. But it's not obvious, right? Looking at this, it doesn't look like X. Let's see what we get. I'm going to continue down on the next line. I'll try to keep this clean. What's my first step? If I gave this to you and I said simplify, what would you do first? I can't cancel these because this is not a factor of the bottom. They've got minus 1 there. Let's get that out of the way first. Those two big parentheses things don't cancel because of the minus 1 downstairs.
You can open parentheses in top.
Yeah,
And then-
correct. I can put this 2 upstairs here, right? 2 over 1 times X over X minus 2. So the numerator.
And then multiply what is on the bottom for X minus 2.
I'm sorry, X minus 2, right? Yeah, X minus 2. We could multiply top and bottom by X minus 2 and distribute. I don't like that though, because there's something that feels like it's violating the order of operations. Remember, the top and bottom of a big fraction are always thought of as being in parentheses. You should think of this like this, always. So if you're going to multiply by X minus 2 top and bottom, you'd have to distribute downstairs. It's just a slightly unnatural thing. What feels very natural to me, here I'm subtracting a fraction minus 1. Well, if I want to subtract fractions, I need a common denominator. So my advice would be, okay, yeah, go ahead and put the 2 up here with this X. That's fine. This is 2 over 1 times X over X minus 2. Downstairs, subtract these by having a common denominator. I'm going to leave the top and bottom in parentheses. And then this is X over X minus 2 minus X minus 2 over X minus 2. And the tops and bottoms of all these little fractions are thought of as being in parentheses. Now I can simplify the downstairs. I've got my 2x over x minus 2 upstairs. And downstairs, I've got x minus parentheses x minus 2 over x minus 2. When we subtract this fraction from this fraction, we're subtracting this numerator from this numerator all over the same denominator.
Where did you get x minus 2 over x minus 2?
I'm rewriting this 1 with the denominator of this fraction here. So in order to subtract these two, they have to have the same denominator. This guy has denominator x minus 2. So
Multiply both sides times x minus 2. Sorry, yeah, I get it. My bad.
No, you're good. You're good. this sort of procedural algebra shit is precisely what gives people a hard time in calculus. This is why we have pre-calc. So any questions you have here, please ask them. There are no bad questions here. Are there any other questions up to this point? I'll tell you what people forget. People forget these parentheses right here. Remember, the tops and bottoms of all fractions are always thought of as being in parentheses. So if I'm going to subtract this from this, if the numerator is x minus all of this numerator. So these little parens here are something people forget. Now, we're almost done simplifying the bottom. The top is still 2x over x minus 2. The bottom is x minus x plus 2, which is 2 over x minus 2. Right, we distribute this negative. The x here becomes negative, the 2 here becomes positive. X minus x is 0x, and then minus 2 is positive 2. I'm going to bring it over here now. I finally have one nice fraction divided by another nice fraction, so I can do the flip and multiply thing. This is 2x over x minus 2 times x minus 2 over 2. We leave the top alone, and we multiply by the reciprocal of the bottom. And again, everything is in parentheses, right? Tops and bottoms of all fractions in parentheses. The x minus 2 factors here cancel. And you get 2x over 2. The 2's cancel. And you just get x. Thank God. So we did the last thing correctly. These are inverses of one another. Technically, to conclude that 100% for sure, we would also need to look at the other composite. I would need to plug them in the other way and show that that also simplifies to x. And like I said at the start, I'm not going to spend class time on it. It takes a while, right? It takes a little while. The specific procedures I went through to simplify this are the ways I choose to think about it. There are other ways to do these manipulations, but you need to make sure whatever you're doing, you're 100% comfortable with it and you understand it entirely. And I strongly recommend you do it the way I do here, because I've found that that works really well. If we were to plug them in the other order, you were to take the 2x over x minus 1 or whatever and plug that in to the other function, it would also simplify to x, and the procedure would be very similar.
Honestly, I thought you would have to multiply 2x and 2 after canceling out x minus 2 instead of dividing them.
Let me hear that again just in 1 second. So we should also check, and say here as a note, should also check that when you compose in the other way, you get x. It will work out. Okay, and then what was that?
I honestly thought whenever you're cross multiplying that you had to multiply 2x and 2 after you cancel out x minus 2 and x minus 2.
Yeah. So if we want to see the little details in the background here, after we cancel these, this becomes 2x over 1 times 1 over 2. When you cancel each of these factors, remember each of these factors is really multiplied by 1. So when you cancel those, the 1 stays here, and this 1 stays here, and then we multiply these two fractions straight across.
So it'd be 2x over 2. Okay.
Yeah, and that's what we did.
So then you multiply them straight across. All right. Well, okay.
Yeah, it's not too bad. So multiplying fractions is nice. You just multiply top with top, bottom with bottom.
It's confusing that it's confusing that it goes from cross. I guess because that's keep change flip. I understand.
It is a little bit weird. But I think with practice, it'll become more comfy. And working with like these big ass fractions within fractions, that's one of those things that we want to get good at before we get to Calc 1, because they show up a lot there. But it's really not too bad, I promise. You can get the mystery resolved. You can get to a place where you always know exactly what to do. And I'll tell you, for me, the big steps there conceptually were to always think of fractions as having their tops and bottoms in parentheses. And also, if you have fractions within fractions, you need to use a big fraction bar, right? The idea is this is the big top, this is the big bottom. If this fraction bar and this fraction bar are the same length and you don't use parentheses, it's actually ambiguous. There would be multiple ways to interpret that because division is neither commutative nor associative. So like 1 divided by 2 divided by 3, unless you tell me which one's the big fraction there, actually has no meaning. Is that 1 big fraction bar, 2 little fraction bar 3, or 1 little fraction bar 2, big fraction bar 3? They're totally different numbers. Hopefully we've helped a little bit with that algebra mystery, and I think the more you practice with it, the better you will get. And one thing you can do for practice is go ahead and compute the other composite here. It'll be very similar. And if you are unable to get it to come out to X, or you're uncertain about any of the steps, that would be a great thing to bring to office hours. Okay. So we were able to find the inverse of X over X minus 2 because it was a one-to-one function. But what if you begin with a function that is not one-to-one? So here's where that step 3 from my 5-step process is going to become important. Let's try to find the f inverse of X. And I'm just going to take the classic example here where f of X is X squared. We know what the graph of X squared looks like. We know f is not one-to-one because the graph fails the horizontal line test. I'll draw it because it's going to be helpful for us to think about. This is what the graph of X squared looks like. And definitely, if you draw any horizontal line up here, it's going to hit that graph in more than one place. So we fail the horizontal line test. Unless I do something kind of sneaky. The sneaky thing that I can do is throw half of this motherfucker away. Just say, fuck it, I don't care about the left half of this parabola. So unless, the term for that is, unless we restrict the domain. So maybe what I say is I want to hold on to just the right half of this parabola. I'm going to throw away the left half. That means I'm going to hold on to the right half of the domain. If you just have the blue curve here, that is one-to-one. If I throw this whole piece away, what that means is I'm restricting the domain to the set 0, infinity. I could have also chosen to restrict to negative infinity up to 0. Either one would be fine. Generally, you want to find the largest subset of your domain on which the function is one-to-one. So from now on, as I move forwards in this problem, I'm going to assume that my function is just this. None of this, just this. On this restricted domain, my function is one-to-one, and I can invert just this piece. So the f inverse I'm going to find here is going to be relevant just to this blue piece, not relevant to this piece. Now let's run through that process. It's not too scary. First I write y in place of f of x. So I've got y equals x squared. and I solve for x. Again, not scary. How do I solve this for x?
Square root.
Very good. We take a square root on both sides. And remember, when you take square roots on both sides of an equation, you get this plus and minus. So if plus minus the square root of y is equal to x. This plus and minus that's showing up in the algebra is the thing we need to be careful with in step 3. So we need to consider domain restrictions. I know in high school they tell you to swap x and y first, then solve for y. Right here is why I say don't do that. Wait to swap them until the end, because your domain has been restricted to 0 to infinity. Does that include any negative numbers?
No. No.
No, right? Yeah, no negative numbers in this set. Now look at what I have right here. This says x equals 1 of plus or minus square root of y. If I pick the minus, then I'm saying x is equal to the negative square root of y. The square root function always spits out positive numbers. So the negative square root of y would always be spitting out negative numbers. And according to this equation, x would then always be negative. But I know from my domain restriction, these are x values, that the x's should always be positive, or at least never negative. So this domain restriction and this equation together tell me I need to take the plus. Since x is equal to 1 of plus or minus the square root of y, and x has to be an element of 0 to infinity, right, i.e. x is greater than or equal to 0, we know that we know to take the plus, not the minus. If I took the minus, then I'd be saying x is always negative, but x is never negative because of my domain restriction. Hence x is equal to the positive square root of y. So when I say you need to pause and consider your domain restrictions and how they affect the algebra, this is what I mean. If the function you're trying to invert is not one-to-one, then you will run into something like this, a plus or a minus, somewhere that you need to choose between. And the way you choose between them is by thinking about the x values that are on your graph. Here you've got this solved for x. So you need to ask, okay, x, should it be positive or should it be negative? Well, since I'm restricting to the non-negative numbers, it can't be negative. It means it's got to be positive. In a more complicated example, it might say, you need to figure out whether x is going to be bigger than -3 or smaller than -3, but precisely the same logic will work. Now we're ready to swap x and y. I get y equals the square root of x. So f inverse of x is the square root of x. And this is very intuitively satisfying. What function undoes the squaring function? Well, it should be the square root function, right? Square roots undo squares. But because the squaring function is not one-to-one, you need to restrict its domain. All right, you guys with me so far? We got questions on this? I would like to now talk about the graphs. And I'm going to help you see this domain restriction business if we chose the other way. So this, you may have seen it briefly flash up as I first opened Desmos, a slightly different example. Here's my original function. It's not one-to-one. But I chose to restrict it to this, to the x's which are greater than or equal to 0. So here is my original function. When I inverted it, let's write g of x for the inverse, we got this guy. And you'll notice some symmetry to the graph, right? The inverse here and the original here are symmetric about the line y equals x. I'll make him dotted. See that symmetry? If I take the green and I fold it over the black dotted line, I get the purple. Functions and their inverses always have this symmetry. This is a characteristic symmetry. In other words, two functions are inverses of each other if and only if their graphs are symmetric over the line y equals x. If I had chosen the other possible domain restriction here, which is this, if I had restricted to x's are less than or equal to 0 rather than greater than or equal to 0, this purple function is no longer the inverse, right? These graphs are not symmetric about that line. That would have meant that when I got to step 3 in my find the inverse process, I would have had to have chosen the other side, the negative square root, because the negative square root does have that symmetry. Look, see? Bullshit, right? For more complicated graphs, this can be a little bit harder to detect. But the stuff I would give you on a test, for example, will be the sort of things you can graph them by hand and see this symmetry or the absence of this symmetry. And that symmetry is at the heart of a theorem that I want to discuss with you now. This is the last thing we're going to do today. This is a theorem characterizing inverses. Characterizing is a funny word. It's like alternate definition of inverse, right? That's what characterizing means. It means it tells you everything you need to know about. The theorem says that the following are equivalent. Theorems of this sort are actually quite prominent in mathematics, especially in analysis, which is like the grown-up version of calculus, right? If you want to go on to take like graduate level calculus, they call it real analysis. TFAEs, the following are equivalent, very common theorems in that field. 1, the point A comma B is on the graph of F. We know that this is equivalent to saying f of A is equal to B. Like if the point 1 comma 7 is on the graph, you know that f of 1 is 7. Thinking about things through the inverse lens, we know that f of A equals B is equivalent to saying f inverse of B is equal to A. Right? This means f sends A to B. So f inverse has to send B back to A. That, however, if we reinterpret it graph-wise, means the point B comma A is on the graph of f inverse. And if you just compare the outermost items, items 1 and 4, A comma B on the graph of F is equivalent to saying B comma A is on the graph of F inverse. What's the relationship between 2 points of this sort? Well, you're swapping the X's and the Y's, right? 1 comma 3 is on the graph of F, 3 comma 1 is on the graph of F inverse. Let's kill these and look at some points. Right, 1 comma 3 and 3 comma 1. I'll label these both red. How about -1 comma pi and positive pi comma 1? I'll label these both green. 4, 2, 3.45, and 3.45, 2. I'll label these both black. Or maybe both. Oh, no, we've already got green. How about both orange?
Why does the -1 turn into a +1? over
It
time?
doesn't. I'm sorry, it doesn't. I just typed it poorly. Yeah.
Oh, good.
Oh, good catch. All right. So look at the colored pairs of points, the 2 orange points, the 2 red points, and the 2 green points. What is the symmetry there? They're both symmetric over this line. That's precisely the symmetry. So if you reflect this point right over this line, you land on this point. If you reflect this point right over this line, you land on this point. And if you reflect this point right over this line, you land on this point. So what this theorem says, the fact that 1 is equivalent to 4 says that the graphs y equals f of x and y equals f inverse of x are symmetric about the line y equals x, because we're flipping x and y values. And that's kind of the point of this theorem. So I could give you the graph of f, and as long as it's 1 to 1, you could use that to sketch the graph of f inverse. You just reflect the whole graph over that line y equals x. Here's a function we haven't even talked about yet. But I can tell you some points on the graph of the inverse. In fact, if I draw in the line y equals x here, you can probably see precisely what that inverse will look like. Here's the original. So the inverse should look something like this, symmetric over that line. And when we talk about logarithms, you will see this. But not for now. We'll get there. That'll come later. The idea is I could give you any original function and you could come up with the graph of the inverse by drawing the symmetric graph about y equals x. That's what this theorem is saying. What's important for you guys regarding this section is that you know what kind of functions have inverses. Those are 1-to-1 functions. You know what the inverse function is. It's the function that exactly undoes the original. You know how to check if 2 functions are inverses. You plug them into each other in both ways and verify that they simplify to x. And you know how to find the inverse of a function. If the function is 1-to-1, you just run through that process and ignore step 3. If the function is not 1-to-1, then you need to restrict its domain and then run through that process. And you should also be comfortable with this theorem and its implications for graphs. That's really it. That's everything you guys need to know about inverse functions at this point. Before I let you go, I know we're probably about out of time, right? Yeah, we're a little bit past. I apologize. I'd like to show, for those of you who are taking trigonometry right now, an important example. Here's the tangent function. Nasty, 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 nasty. Blows up to infinity all over the place and is very much not 1-to-1, right? This fails the horizontal line test so badly. In fact, it's infinity to 1. Every output gets hit by infinitely many inputs. But if I restrict its domain from -π/2 to π/2, that becomes a 1-to-1 function. And if I think about reflecting that function over the line y equals x, let's get it here in a different color, dotted, then I'll get the graph of the inverse tangent function. Which looks like this. And again, symmetric about that line. If I throw away this restriction, then I cannot invert. But with the restriction, I can. And the desired symmetries are present. Every one of your trig functions is going to require some special domain restriction. Just like when we inverted x squared, I had to restrict the domain. When you invert any of those trig functions, you're going to have to restrict the domain because they're all periodic. They're all infinity to one functions. So that's probably your most important application of this material in the immediate future. But I tell you, there are many, many places in Calc 1 where we talk about inverse functions, many more in Calc 2, not so much in Calc 3. But this concept of restricting a domain to get the existence of an inverse and then calculating it, and then later things like its derivative or antiderivative will be big. This is the last bit of material that's going to be on your test. You have a homework and a quiz, which are relevant to this, open and available and WebAssign now. If you get stuck on anything, you can come see me either in office hours or you can send me a Canvas message or an email. Like I said at the start, I'm still getting through emails. I got like 50 of them last night. So if I haven't gotten to yours, I'm sorry. I'm doing my best. My goal is to get everything cleared out today. Are there any burning questions for me before I let you guys go? I know, Soraya, we wanted to talk a little bit. So everybody besides Soraya is welcome to leave. And I will see you guys on Thursday for our test. All right, make sure you're working hard. If you get stuck on anything, Canvas message, post to Discord, or come by tomorrow's office hour.
Thanks. Have a good day.
Yeah, you too. So Soraya, if it's okay, I'll just talk to you in the chat here. So keep it reasonably private. Now, I'll remind you, Soraya, we talked about this at the very start of the semester. If you feel like you're in a place where there's the only way you could make this test go well is to do something shady, not that I think you're planning to do that, but if you feel like you're kind of trapped like that, you can let me know and I can put you into the cohort for the makeup test, which will give you a few more days to prepare. The makeup for this class would probably be next Tuesday rather than this Thursday. Okay. Yeah, I will be. So right at now, as soon as I finish this, I'm digging into my email. So I'll do that. I'll definitely be able to reply to you there. And then if you do feel like, tomorrow the day is coming to an end and you really don't feel like you're in good shape, just send me another message saying, hey, can I please be moved to the makeup group because there's no way I can make this work out. And I have no problem doing that. I would much rather that than you feel trapped or stuck. Just be aware that in the time between now and that test, when you actually do take the test, you gotta be working very, very hard. The time is good, but it only helps us if we're able to like sink that time into preparing. So I would say spend time at the Learning Commons. If you can go there in person, that's best. But if you can't or don't want to, I understand the online stuff is okay. They're getting better at it. And then come to each of my office hours between now and when you actually take the test. That way you and I can work together. That will be most helpful. All right, and I will reply to your email. It's just going to take me a little bit of time to get to it because I've got so many. Posting those same questions, if you've got the list of questions, whatever you sent to me, whatever else you're thinking of coming up with, post that to the Discord also, like pictures. of the work, pictures of the problem. There are other people in that Discord from my other 1140 classes that can help you out, and I also check those out and try to respond. Oh, if you saved the server, it would still be there, but the invite links do expire every week. So let me create a new invite link here for your group. There it is. All right, invite, copy link. Okay, so I am going to update. If you go to our go to the announcements in our class in Canvas, and then go way back to that Discord announcement, I'm updating that link now. So definitely work with the tutors, and also consider working with the with your classmates in Discord. All right, there it is. The Discord link is updated in the announcements. Send me an email letting me know what you would like to do with respect to the organization of the test, timing and stuff. And then come by office hours as much as you can, work with tutors as much as you can, and I'll do everything I can to help make sure this goes well for you. Just remember, you got to be syncing time in. We're talking like 2-3 hours a day minimum between now and when you take the test. All right? Cool, cool. All right. I'll look for your messages and we'll move forwards like that. Take care.